things I want to talk about today. The first is how to deal with multi-byte arithmetic, and the second is a little bit more about hardware interrupts and that sort of thing. Okay, so if we look at the schematic on here, there's a couple details I want to go into. Okay, the first is on the processor. Okay, we have this line here, pin 4 on the processor called IRQ, and it's got a bar over it. Okay, so what that means is that if the IRQ is tied high, then the processor never gets interrupted. Okay, there's just no interrupts, period. We similarly have a second type of interrupt, which is the non-maskable interrupt, and we'll talk about the difference between those two things in a moment. But basically, in this schematic, Ben has us tying the non-maskable interrupt high, which means that a non-maskable interrupt never occurs, because the way you trigger an interrupt, maskable or otherwise, is to bring either the IRQ pin low or the non-maskable interrupt pin low, one of the two. Okay, so under what conditions do we want to trigger an interrupt? And really, what is an interrupt, broadly speaking? Okay, so if we've got a program that's doing a bunch of stuff, an interrupt is a situation in which whatever the program is currently doing needs to stop temporarily so that we can deal with something that's of a higher priority, deal with it, and then return to wherever we were in program execution and continue working. Yeah. Okay, so in a video game, what would be a situation where we need to have an interrupt? Huh? Okay, in a video game, it's actually going to be a lot more than you think it is. Okay, a pause button, yeah, would technically be an interrupt. Okay, where you could go into like an endless loop that just sits there until you hit a button or something. Okay, but every time that there's, well, okay, it actually depends on how you set this up, but you could configure things to interrupt anytime there's a button press. Okay, so if you're playing Mario or something, right, and you press a certain button or buttons, then you would want that, for example, for it to trigger an interrupt, for the program to then register, okay, what button or buttons did you just press? And then when it returns to game execution, it should know or do something based on that, okay? Now, in the case of games like Mario or something, for example, there is also another way you could do it, which is you could poll the controller very, very frequently. For example, every horizontal scan line or every frame of video, you could check to see whether or not buttons are being pressed. Okay, probably not a very efficient way to go, but in some games where you're expecting button presses to be happening all the time anyway, that might actually be more efficient than doing the interrupt method. Okay, yeah. So in our case, right, what we might want to do to, for example, trigger an interrupt is we've got this screen and we've got some buttons, okay? And one of those buttons is our reset button, okay? So we'll leave that alone. And then obviously we've got the clock module, so we'll leave that alone. But we'll take the case of the other 5 buttons that are in the schematic and in the way you built it, attached to the the 65C22, okay, the versatile interface adapter module. But they don't have to be there. It's just they're there for in his schematic for a good reason. Okay. Now, one of the things that's somewhat limiting about the 6502 architecture is there's really only 2 interrupts. There's the non-maskable version, and there's the maskable version, or IRQ, okay? And in terms of the software to handle an interrupt, what happens is whenever this interrupt pin goes low, that triggers an interrupt, okay? And the processor is going to do a couple of things whenever it detects an interrupt. The first thing that it's going to do is complete whatever instruction it was currently executing. You don't want to interrupt mid-instruction. That doesn't make sense, okay? The second thing it does is it takes its current value of the program counter and its current value of the flags register, and it pushes them onto the stack. Okay, and that makes sense because when we want to return to executing things the way that we were, we need to know where were we when the interrupt occurred and what were the flags when the interrupt occurred so that we can reset those just before we go back and resume execution. Okay, and then we need to decide, well, where do we go under the situation that an interrupt occurs, okay? There is only one location in code that you can go for this, okay? There's two locations, one for the maskable interrupt and one for the non-maskable interrupt, okay? So for that, let's go back to, let me go back to the 6502 data sheet. Okay, and now this is contrast a little bit with other computers. So those of you guys who did the operating system course with Dr. McCartan Lim, you had a whole bunch more interrupt vectors than this, right? You guys had like a whole table of them. And Rippy is crying from trauma, right? But okay, so these are the vectors that you have at your disposal. Okay, so an interrupt request, the vector or the location of code that you should start that the processor should jump to under the situation of an interrupt. You need to put that memory address in the interrupt vector at FFFE and FFFF. Okay. Similarly, the reset vector we put at FFFC and FFFD, and for our case on the breadboard stuff and most of the 6502 things, where is our reset vector going to point to? So what would we put in FFFCD? We put 8,000 hex, right? Because where did our code start in memory on the breadboards? Address 8,000 because that was the very beginning of the EEPROM, okay? Okay, and when we hit the reset button, what happens is the processor does some initialization stuff, and then it loads what's in FFFC and FFFD as its reset vector and jumps to that location to start loading in program code and executing. Okay, but that's hardwired for it to always look at FFFC and FFFD for that reset. Okay, similarly, it's hardwired for the interrupt. So when an interrupt gets triggered, it's going to finish the instruction it's currently executing. Okay, that makes sense. Once it's finished with it, push the current value of the program counter onto the stack along with the flags register. Okay, and then it's going to load and jump to whatever address is stored in FFFEF, okay? Our interrupt vector, okay? And it's going to go to whatever that memory location is, and that memory location is where we're going to put our interrupt handler, or one of our interrupt handlers, which will be a special segment of the code that is designed to deal with, okay, an interrupt just got triggered, now what? Okay, what am I supposed to do? And there are two versions of this. There's the interrupt request, which doesn't have to be dealt with immediately. And there's the non-maskable interrupt that must be dealt with immediately no matter what. Okay, so you want to think of like non-maskable interrupts as being absolute showstoppers that under all circumstances you must deal with them right this instant. And regular interrupts for anything that's not quite that important. Okay, and in the case of Ben's breadboard design or the equivalent PCB design, In those cases, there is no non-maskable interrupt because we tie the NMI pin high, and therefore we never trigger a non-maskable interrupt. Okay, but we can trigger regular interrupts. Okay, good. Okay, so in our case, we're going to define a label in our assembly code for IRQ. Okay, and that will be wherever it is. And then at the end of our program code where we define what the reset vector and that sort of stuff is, we'll just say, okay, FFFE and FFFF need to be whatever the reset, or sorry, not the reset vector, the location of the interrupt handler, and then the assembler will sort out the actual arithmetic for us. Okay. Okay, good. Yeah, okay. Now, to contrast this a little bit, so like the guys who took the OS class last year, right? How many reset or interrupt vectors did you guys have? You had a whole bunch of them. Okay, you also had a much bigger memory pool, okay, because the architecture of the 8086, sort of, right? Right. Well, so you in memory on the floppy, you were essentially limiting yourself to 640K of RAM, right? That was the memory model that you were working under. Okay. Right. So you had very limited memory. Okay. But on that architecture, though, you had the ability to have multiple different kinds of interrupt vectors. And the hardware was capable of determining on a hardware level what caused the interrupt, right? So if you had an interrupt that was due to a keyboard press, you knew that that was different than if the interrupt had been triggered by some other device. Yeah, and with the 6502, we don't have that ability. Okay. No. So what all that you can do with the interrupt vector is know that an interrupt has occurred. And then within the interrupt handler, completely in software, or almost completely in software, then you have to figure out who triggered the interrupt. Okay, yeah. Why don't you define PIT for everybody first? Yes, that is possible, because the 6522 does have a couple of timer circuits in it that you could use. Okay. No, not quite. No. Oh, okay. Yeah, you could actually tie the clock to the interrupt pin, and yeah. So let's say, for example, we had a second clock module, right? We just built a clone of the clock modules we already have. Okay. So what Rippy is suggesting is that we have one of the clocks control the processor, right? Just like normal. Okay. And then we put the other clock and actually tie it to the interrupt pin so that every particular amount of time we're triggering an interrupt, right? Okay. We don't have to actually do it that way, but you could. Okay. So now, why would you want to do that, though? Essentially, what you'd be doing is what I said before, which is periodically checking to see, I'm going to interrupt to see if I need to like do something, right? That would be equivalent to just polling the hardware that might cause the interrupt to see what its values are, right? So for example, I could poll my buttons and see, have the button status changed in any way, okay? Uh, yes and no, right? It could be very slow in the sense that you're dedicating a large portion of your execution time to some other thing, okay? But you have to remember, of course, that if we were to clock this processor for realsies at 1 megahertz, then that probably won't matter, okay? And for the kinds of, like, given the hardware that is on board the breadboard project, right, what do we have? Other than the processor, we have the screen and we got some buttons. Like 1 megahertz is overkill for this kind of thing, okay? But the processor can operate that fast, so well, we might as well do it. Okay. Um, okay. So um, the what Rippy suggests is not, in fact, how we're going to do it, because the timers that you could use for this actually are already built into the 6522 module. Okay, and so there's no need to build a separate module for that. Okay, but there are other reasons under which we might want to trigger an interrupt. Okay, and for that, let me go back to the schematic. Okay, so Ben has two videos in his playlist on the interrupt department. Okay, the first one is called Hardware Interrupts, and the second one is called Interrupt Handling. Okay, watch both of those, please. It's just an output of the clock, so you could, yeah, but we don't use that.
Could you tie that to the interrupt?
I wouldn't.
That would cause an interrupt very frequently.
Yeah, oops, let's see. Let's open that in a new tab. I wouldn't. Okay. Okay, so I mean, you could, but I wouldn't. Okay, so an interrupt gets triggered whenever the IRQ line gets brought low. Okay, so what Ben does in his first video is he says, okay, earlier on in the videos, he actually just tied this IRQ line high so that interrupts never got triggered. Okay, and then to start demonstrating what's going on, he just said, okay, let me just put a button in here, kind of like our reset button. Okay, and I'll have a resistor so that it's tied high unless I hit the button, in which case it's shorted to ground, and that will bring the IRQ thing low, which will trigger an interrupt. Okay, and then in his case, he has something that when an interrupt gets triggered, it adds to a counter value and it displays that counter's value onto the screen. Okay, on the breadboard. Okay, now what you immediately notice, though, after he gets it all wired up and stuff, is that when he hits the button, what would you expect the screen to show if he triggers an interrupt, and let's say that the screen's value starts displaying a 0? He hits the button, an interrupt happens, it displays 1. You would expect it to display every time you trigger an interrupt, the counter gets upped by 1, and the screen is going to display whatever this counter's value is. So you would expect when you hit the button that the counter would go to 1 and you would see 1 on the screen. But that's not, in fact, what happens. Okay? And the reason is because if you hit the button, what's happening is the processor is interrupting, updating the counter, interrupting, updating the counter, interrupting, updating the counter. So the longer you hold it down, the more interrupts are happening. Or if you're operating it at a high frequency, like in his videos, he's using the 1 megahertz clock. So it's like thousands, right? And even if you just try and barely tap the button, you still get hundreds worth of interrupts because the thing is just operating that quickly. Okay. Okay. So that clearly is not the way that we want to deal with the interrupts. We want to have something because we don't want it to be triggering hundreds of them when we just want to read it once. Okay. So what we want to do instead is take advantage of the fact that we have this auxiliary processor in the 6522. Okay. And so then as he continues the video, that's exactly what he does. Is he said, okay, let's actually use the 6522 as sort of a mediator, if you will, in the interrupt department. Okay, and what we'll do is we'll have, when an interrupt gets triggered, we'll figure out, okay, what caused it, and before we stop servicing that interrupt, we'll say, okay, got the interrupt, turn the interrupt flag, or sorry, clear the interrupt line so it goes back high. We've dealt with the interrupt and it only triggers once. Okay, so we trigger it, and then while we're dealing with it, we say, okay, we got it. You can clear the interrupt flag, and then resume operation, and the counter would only actually get upped by one. Okay, so that's sort of the idea, and you guys will see when you watch that how he sort of approaches it. Okay, now the way he approaches it actually though is, let's look at on our schematic here for the 6522. What stuff do we have on it? What pins? Well, we've got kind of the input side and some output stuff going on, right? We've got our data bus in, that's D0 through D7, and then we've got two 8-bit lines. We've got the A bus, that's PA0 through 7, and the B bus, that's PB0 through 7, okay? The B bus is tied completely to the display, and some of the A bus is tied to the display for the control lines of the display, okay? That basically make the display do what it's supposed to do. Okay, that leaves us with 5 unused A pins, A0 through A4, okay, which he says, okay, got to put something there, so let me wire up some buttons. Seems like a reasonable thing to do. Okay, so he wires up 5 buttons, one to each of them. Okay, but in the interrupt video, what he actually does is he uses a single button and he wires it up to this pin CA1. Okay, now in the schematic, what is CA1 wired up to? It's left floating. It's not connected to anything. Okay, which means it's not actually used. Okay, and after many hours on both Reddit and digging through the manuals, I'm pretty sure I've figured out exactly how this works. Okay, basically, under what conditions does the 6522 trigger an interrupt? Okay, so on the 6522, there is a pin for interrupt request, okay? And this means that chip can bring the interrupt line low, okay? If the 6522 brings it low, it is signaling to the processor, hey, interrupt, okay? And the 6522 is generating that interrupt, okay? So it's the one causing it, not receiving it. Make sense?
So it gets the request from the other chip.
The 6522 is the one that generates the request, and the processor reads that. Okay. Yes. Okay. And in our case, there's only one 6522 on this machine, and therefore it is the only thing capable of causing an interrupt if everything is wired according to the schematic. Okay. Okay. So we got that, right? All right, so under what conditions does the 6522 trigger an interrupt? Yeah. The IRQ pin on the 6522, it is signaling to the processor, hey, I need you to do an interrupt, dude. Well, okay, because, so the whole point of the 6522 is to connect, to sit as a mediator between a processor and auxiliary devices, okay? Those could be things like disk drives or our display or buttons, or instead of directly to the processor. Exactly, okay? And you could theoretically have lots of these, right, 6522s. Okay, the Commodore, I think, has 2 of them, if memory serves, along with 2 things that are very related, which are called the 6521s. Not for a breadboard thing, no, but for a full-blown home computer, yeah, we would need more of these things. Okay,
You need like one for every
kind of peripheral
and these are not like interrupt request for every IO bus.
device,
You're gonna have like
a bunch of them.
yeah, you're
Yeah,
gonna have one per key to like identify like that you identify.
you wouldn't need a single chip for every single key, but you would need something that could handle the keyboard,
Yeah,
right?
so that you can read it.
So that you could know not only was a key pressed, but then also be able to determine which key got pressed.
Not for the 26 letters. There's not going to be 26 different keys.
No, no. Um,
You want the entire keyboard.
yeah, you'd probably need one chip for the whole keyboard. Okay. And then maybe the keyboard would have its own sort of special uh, thing to then sort out like which keys were being pressed or whatever. Okay. So, yeah, you would need one of these things for basically every pair roughly of peripherals because it's got both it has an A line and a B line, so you can kind of put two peripherals on one chip, right? And in our case, the way that we're using it is basically our two peripherals are the screen and some of these buttons. Okay. Our buttons are sort of input peripherals, and our screen is an output peripheral, right? That's fine. Okay. But it could be things like keyboards or serial ports or the floppy drives or the video card or all kinds of other extra thingamajigs. Okay. Okay. So, uh, under what conditions does the 6522 generate an interrupt? Is essentially the question, right? So when is this chip going to bring the interrupt line low to signal to the processor, hey, hold up, I need you to deal with an interrupt? Okay, that's the question. All right, to answer that, we need to go back to the data sheet for the 6522. Okay, and also watching his videos will explain a little bit of this. Okay, so there's a whole bunch of stuff on this thing. Okay, um, this is a versatile interface adapter, is what it's called. Okay, um, and the Commodore, like I said, I think it's one or two of them. It also the Commodore also has two other chips that are called complex interface adapters that are similar in spirit to this thing, but a little different.
A lot of these are like a big one.
Yeah, okay. So a PlayStation, okay. So this is one of the things about more modern computers is that these these chips tend to become more monolithic, where a single big chip handles all of these sorts of functions. Okay, and so on the original Commodore, though, you had a lot of these sort of purpose built chips and you put multiples of them together, whereas on a modern processor things are a lot more integrated together. It's kind of like another way to think of it is how many of you guys have built your own PC in the last say 5-10 years?
Yeah,
Unfortunately.
Well, and when did you dumpster dive to build your PC?
back in like 2013.
Okay, yeah.
It's
So
still
I try.
beautiful.
but point being, like, if I wanted to build a computer today, okay, yeah, I'd need a motherboard, I need a processor, I need some RAM and whatnot. But would I need a sound card or a
No,
network card? Why not?
because they're already
Because
there.
they're built onto the motherboard, right? Well, that didn't used to be the case,
You used to have Ethernet
right? You used to
cables.
have to get your motherboard. You would have a sound card, you would have a network card, you would have a modem, you would have a graphics card. You had all of these different cards slotted into the things.
That's like when you're like building Frankenstein. Instead of just getting like a whole arm and a hand, you have to like get like an arm, part of the hand, finger one, finger two, finger three, finger four.
Yeah,
finger
but that's how
five.
it used to be.
Were
Ew.
there any benefits like to doing it that way versus now it's all integrated
Uh,
automated and stuff?
to some extent, yes. So the benefits would be, well, okay, it was sort of done by necessity back in the day, okay, because each of these things was a separate module and they were all complicated enough that they had to be manufactured as such. And so the benefit then is that your motherboard is simpler and therefore not as expensive. So each individual unit is not as expensive to produce as one monolithic unit that does everything. And it was just not feasible in the mid 90s, for example, for all of these things to be monolithic.
What's the point of a sound card if you don't even need sound?
Well, and that's the other part, right? Is that like in the 90s, right? When you bought a computer, well, you didn't necessarily need sound, okay, or networking, or a modem, or, now you needed video, sure, but in most cases, right? Um, and so you would just pop in the cards for the functions you needed, okay? And it might be the case though that you weren't always using all of them. So for example, my computer in the 90s, right? I had, well, this is kind of crazy. At one point I actually had two graphics cards. You had a 2D card and then you had a 3D card, and those were separate products. Okay.
Wait, is it just 3D, or is it 2D just basically 3D without an extra plane? So why would you want like a 2D?
Because the way the architectures were, you had to have a 2D card for Windows and stuff, and then you had a 3D card for your games, and they had to be tied together.
I think I remember we talked about.
Yeah, they were dark times, Rippy, dark times. Okay. Um, yeah, okay. So you had a 2D card, a 3D card, a sound card, a modem, a network card, and I think that was all of them. Okay. And then your hard drives and stuff plugged into the motherboard, and there's usually a disk controller on board the motherboard. But yeah, there was 5 slots worth of stuff. And one of my first cases didn't have enough slots. So if I went to a LAN party, I had to take my modem out and put the network card in because there wasn't enough slots for it. Okay. Um, yeah. So anyway, back to the 6502 stuff, right? The Commodore, or other computers of this era that use this kind of processor, or the Nintendo or whatever, right? They would have to have the appropriately selected number of these sorts of chips in order to handle the peripherals that they might be dealing with. Okay, the Nintendo was a little bit simpler in the sense that it was not nearly as expandable as, say, the Commodore was. It was never designed to be, right? The What was the expansion you could do with an original Nintendo? Well, you had controllers, you had the game,
Game chips.
and that was it, right? There was nothing else you could expand it with. Now, the Japanese version did have a little bit more expandability, okay? And in fact, it was possible to buy a floppy drive for your Famicom, okay? They call it the Japanese NES, right? That's what they called it in Japan, was the Famicom, for short for family computer, okay? So you could get a keyboard, you could get a floppy drive, and there were like vending machines, basically, where you would take a floppy and you could buy a copy of a game to put on your floppy, and it was cheaper than buying a cartridge.
So it's basically the equivalent of now how we download games.
They had DLCs. You just had to go to a vending machine someplace.
Except it's not cheaper when you download it.
Well, now, no, it used to be. It
Well,
used to be cheaper when you got it on the internet versus in the store, and then now everything's totally priced.
yeah, because they're going to get your money no matter what, right?
Unless I choose to just go on the Pirate Bay, steal it all.
Okay, we're on a stream. No, we're not talking about.
For legal purposes, not as a joke.
Yeah. Okay. Okay. So you would have several of these, and the Commodore has, like I said, a couple of other chips that are called 6521s. They're similar in spirit to this thing. The 6521s, amongst other things, handle the keyboard and the disk drive. Okay, which is now one thing that's really annoying. They don't make the 6521s anymore. They do still make the 6522s. Okay, this is a big problem in restoring old Commodores because if the keyboard's not working correctly, 99 times out of 100, it's because of a bad CIA, complex interface adapter, which is the 6521 chip. Okay, and they don't make them. So where do you get the working ones? From other Commodores, right? You have to Frankenstein these things. Okay, and so the supply of these things is dwindling. Okay, anyway, so under what circumstances does an interrupt get triggered by this chip? That's the big question. Okay, there are some timers. I don't want to talk about those, and they can generate interrupts. There is also a shift register that you can use to do things. So what a shift register is for is basically if you have serial data coming in and you want parallel data going out or vice versa, you use a shift register. Okay, and yeah, okay. But we've got interrupt flag register and interrupt enable register. Okay, so those are two registers that allow us to decide what interrupts are going to happen. And let me go find where the read handshake control and write handshake control. Okay, so there's control things here. Okay, and for CA1 or CA2, okay, you can have positive active edge or negative active edge triggered interrupts. Okay, so what does the positive versus negative active edge mean? Well, whenever you have a level change in a circuit, the voltage is either going to look like that or like that, where it's going to go from low to high. So that's kind of from a logical 0 to a logical 1. This is the positive edge, and that's the negative edge. Yeah, that's just what it calls it, right? Okay, so it's the rising edge or the falling edge of a signal change, okay, from either a 0 to a 1 or a 1 to a 0, logically, okay? Now, the CA1 and the CB1, those are basically single things, okay, and they can be configured to trigger an interrupt under the circumstances of either a negative or a positive active edge. Okay, the CB1 CA2 and CB2 can have a little bit more complicated control. Okay, and so what we can do is use the CA1 line to trigger an interrupt, and we would just need to set the appropriate bit of a register to either a 0 or 1 based on whether or not we want the interrupt to be triggered on the rising edge or on the falling edge of a data change. Okay, and we'll have to then think about, well, which one do we need, rising or falling? Okay, and that will depend on some things, which we'll talk about in a minute. Okay, good so far? Okay, so if an interrupt is triggered, okay, so this goes through timer operation. You guys can read that. Blah, blah, blah. I don't want that. I want the interrupt stuff. And I may have gone a little bit too far here. Here we go, interrupt operation. Okay, so what happens when an interrupt is triggered, okay, is an interrupt can be triggered for a number of different things on this chip, okay? And there's an interrupt flag register, which has 8 bits, okay? And there are multiple things on the 6522 that could have caused the interrupt, such as the timers, the shift register, or this CA1 and CA2 or CB1, CB2. Yeah, I guess, technically, yeah. Yeah, okay, so under what circumstances are is an interrupt triggered? Well, that's going to depend on what we do. Okay, so we won't use the timers necessarily, okay, nor will we use the shift registers, and we're not going to use the CB1 or CB2, okay. What we'll use actually is CA1, I think, is the one that we want to use for this, okay. And so if I have a either positive or negative edge on CA1, depending on which way I configure it, what that will do is when it occurs, the processor will set the appropriate bit to a 1 to say, hey, something just happened on this device, okay? And the IRQ, this bit here, is going to be the logical OR of all the 7 bits before it. Okay, so if the 7th bit here is a 1, that means that somebody in the previous list is a 1, which means somebody just triggered an interrupt. We don't know which one necessarily yet. We'll have to do extra work, but somebody triggered it.
So like if you just you want to use one, you want those interrupts, they ignore all of the others. Is that IRQ thing gonna get triggered regardless?
No, because you can also disable or enable whether or not other devices can trigger it. So in addition to the interrupt flag register, there's an interrupt enable register where we could say, okay, I'm going to disable interrupts from everything except for CA1. And that way I don't have to worry about that.
Because I was like saying, if the IRQ goes off every single time, one of those the timer's gonna collapse.
Well, but yes, and so what we'll do is we'll turn off the ability for certain parts of the 22 to trigger an interrupt and only turn on the ones that we care about. So if we were to use the timer, we'd obviously need to turn on its interrupting ability. Okay, yeah.
Do you mind explaining CA1, CA2, and ORA?
Yes. Okay. So what ORA is? ORA is output register A. Okay. So so let me go back to the schematic for just a second. Well, actually, no. So there's these peripheral lines, right? So we've got the A lines. There's 7 of them, or 8, excuse me. Okay, and the B lines. There's 8 of those, right? On the 22. Okay, so there is a little internal register that stores the data. So let's say that I've got 8 things connected to or like let's say my screen. Okay, I've got 8 data lines running to the screen, and I want to pass 8 bits to it, 1 on each of those lines. Okay, then there's a register inside the 6522 called ORB, output register B, and if I want to put data on the appropriate data lines, then I write to this register, and writing to this register sends it out to those pins. Okay, so if I want to trigger an interrupt using CA1, I'll trigger it, and how do I clear the interrupt to say, hey, I've dealt with it, by either reading or writing to that register. In our case, it'll be a read, okay, because we're using buttons. Okay, and so what'll happen is, and this we're going to have to make some modifications to Ben's circuit, is basically when I hit a button, a couple of things are going to happen. 1, an interrupt is going to get triggered. 2, the output register, well, actually it'd be the input because we're going in rather than out, but will latch whatever data is being presented to it at that moment that the interrupt was triggered. Okay, so when I hit the button, I've got 5 buttons, and maybe some of them are being pressed and others aren't. Okay, an interrupt gets triggered, and it's going to latch, okay, these ones were pressed and these ones weren't. Okay, and then when I read from this register, I can say, oh, well, the bit pattern in this register is blah. And since I know which bits are in which positions, I can say, okay, the first and the third button were pressed, and then do something in my program based on that information. Okay, and in doing so, what this will do, but when I read that register, it will clear this interrupt flag, and that basically says, all right, 6522, I see you, I've dealt with the interrupt, you can calm down now, and we can all resume normal operation until a new interrupt gets triggered, and in which case we'll deal with it. Okay, so this is how you prevent the situation in his very first video on interrupts, where when you hit the button, the counter actually goes up by hundreds. Okay, because it was basically interrupt, clear, dealing with it over and over again, because no matter how fast you press the button, you're not pressing it at 1 megahertz, right? Okay, so does that kind of make sense, sort of? No. Okay, so let's go back to the schematic, because there's a problem. So what I'm saying is that in order to trigger an interrupt, we need to have a level change on the CA1 pin, or the CA2 or CB1, CB2. Okay, can we have a level change on any of those pins? Why not? Nothing's attached to them. Okay, so the way Ben has this thing drawn, okay, is here's our buttons, okay, oops, and he has the buttons tied to resistors, pull-up resistors, okay, so that's these guys here, so that when you press the button, it shorts to ground. And so if you're not pressing a button, you're reading a 1, and if you press the button, you read a 0. That may feel backwards, and it kind of is, but that's okay, right? We could always invert it logically in the processor, okay? But the data lines there, so for example, PA0, okay? Under what conditions is PA0 going to be a 1 if I am not pressing the button? If I press this button, then PA0 will get pulled to ground, which is a 0. Okay? Does that make sense? Okay, so yeah, it does feel a little backwards, but that's okay. Like, we can always negate things. It's not a big deal. Okay, so we want to be able to have these buttons trigger an interrupt. And what I'm claiming is right now they cannot. Okay, because what are the ways that we can trigger an interrupt on the 6522? We just looked at it. There has to be a level change on CA1, CA2, CB1, CB2, the shift register, or the 2 timers. Okay? Are these buttons going to do any of those things as currently diagrammed in this schematic? No, they will not. Okay? So we have a few options. Rippy suggests more buttons. I'm going to suggest something maybe a little bit more complicated, but then in the end will be simpler. Okay? Okay, so we could put a button here on the CA1 line. Okay, and if we did so, anytime we hit that button would signal an interrupt. Okay, do we want it to be, though, that we have to hit this button to signal an interrupt? No, we want to just be able to hit one of the buttons that already exists. Kind of. So what I want to do is I want to tie all 5 of these buttons into CA1. But I can't just tie all 5 buttons into CA1. Well, kind of. Okay, or better. Okay, you can't use a diode. Okay, and there's a reason, and that means we have to go back to the data sheet. Okay, so let us continue, and let's look at one thing that it says here, the interrupt buffer. Okay, so the interrupt thing, and the CA1 stuff, right? Actually, this is not what I wanted, not this thing here. It's a little further, but it looks similar. Let's see, where does it have the bit about?
You can't take 5 diodes, put them all pointing out of the same line.
Nope, because what that is called is wire ORing, and you can't do that. You have to do logical ORing. Because the data sheet says not to.
any of them turn on, it'll signal one of the pins to be on.
Okay. Yeah. So the IRQ. So okay, the difference between these two diagrams, right, is so the original 6522 and 6502 and all of those dudes were all fabricating using an NMOS process. Okay. And so essentially they were using N-type transistors, only N-type transistors. And the reason that processors back in the day were made using those only is because those ones worked faster and were more reliable to manufacture at the time than the P types. Okay. Later, the fabrication technique got to the point where the P types were also good. And the best way to do it is actually to pair them. Okay. And this is called CMOS, complementary metal oxide semiconductor. So for every P, you have an N and vice versa. Okay. They come in pairs. Okay. The original NMOS chip, its interrupt thing looked like the dude over there. And on the other side, on the new CMOS version, it looks like this. That gate, basically what you're seeing is how you do a metal oxide semiconductor NOT gate. Okay, so IRQ comes in as one level and the negation of it goes out as IRQB. Okay, so yeah, that's how you do a NOT gate. Okay, but in here it talks about, okay, this thing here is called a totem pole configuration. Okay, all right, so the WC6522S, which is the kind of chip we have, IRQB signal was meant for logically ORing rather than wire ORing IRQs of a system. Okay, so what that means is if you had multiple ones, multiple 6522s, you would not use diodes coming off of them to go into the processor's interrupt pin. You would use OR gates or AND gates. Okay. Why? This change was made to improve the low power, high speed characteristics of the parts. Okay. For systems that have wire ORed interrupt request outputs, a solution is to place a low voltage diode in series with the totem pole output. Okay. They did it because it meant that they could speed things up. Okay.
So by putting it into a logic gate instead, like an OR gate, which is basically equivalent to what's happening, is going to speed it up.
Yes. And you get the other part is low power.
That's important.
Okay. Right. So that's why they did it. Okay. Now that's on the output side. On the input side, okay, we should do the kind of the same thing, basically for the same reason. Okay. Now, if we think about, so let's go back to the schematic, right? Because what we're looking at now is not the output part, but the port A or port B kind of things. Okay, CA1 or CA2. Let's see, where is it? CA2, CA2, CB1, CB2, CB1, CB2. Yeah, and then it's got various other versions of this. Okay, so let me go back to the schematic here then. Okay, so we basically want CA1 to get pulled. Well, that's up to us actually. We want CA1 to change to get pulled, let's say pulled low. Okay, under the situation that one of the buttons, some button got pressed. And if CA1 stays high, then that means nobody was being pressed. Okay, so we need a logic gate for this. Okay, or actually a bunch of them, but which one do we want? Or and, okay?
Wouldn't you want an AND gate when all the AND gates are tied to the same thing?
Well, okay, it depends on which way we do the logic, right?
You could use an OR gate for a lot of.
We could use either an OR gate or an AND gate, okay? And the difference is basically just which way we think about the logic. Are we going to have the buttons pull low, which they do, Okay. All right. So if I were to take basically, if I were to imagine wiring all 5 of these things to the CA1 pin, okay?
Okay, so is this the time where we take, are we going to take 5 AND gates, or can I just take all of the inputs and put them into one?
The former.
AND gate? So you need 5 AND gates.
Oh, okay. That depends on what kind of AND gate you have, okay, or OR gate for that matter. So what kind of AND gates or OR gates or XOR gates or whatever do we have at our disposal? What's up there in the lab? Okay, we've got some 7400 series ICs. There's piles of them, okay? But what types do we have? They make a lot more than we do have, obviously, but what do we have? 2 input, single output. And there's 4 of those on each chip, okay? So if I have 5 buttons, what are we going to have to do? We're going to have to do button 1 and button 2, and almost like a March Madness bracket. Okay, and button 5 gets a bye. Okay, so here's gate number 1, and we'll figure out if it's AND or OR in a minute. Gate number 2. All right, then these 2 guys need to go into gate number 3. Yeah, I guess it is, right? Okay, into gate number 4. Well, okay, and determining whether or not we want AND or OR just is going to depend on the logic here. Okay. No, if it's pressed, it'll be off because these are pull up resistors, not pull downs. Okay. And that's what this needs to do.
Because if you make it an AND button, if you press any of those, it's going to make a cascading false state, which will turn them all off.
Yeah, exactly. Okay. So let's suppose that we are pressing none of them. Okay. Then what that means is all 5 of these data lines coming into PA0 through PA4 are logical 1s. Okay. Because how are the buttons wired? Okay. If I press the button, what happens? It shorts it to ground, which means it's read as a logical 0. If a button is pressed, it is read as a logical 0. Okay, so let's suppose that we use AND gates there. Okay, so basically this is the question, right? Should we use AND gates for all of these, or should we use OR gates? It needs to be AND in this case because the logic type, we're going 0 when pressed rather than 1 when pressed. Okay, so let's suppose that no buttons are pressed and we have AND gates. Okay, that means all 5 of these inputs are 1s. And if I AND up a bunch of 1s like this, what do I get? A 1. Okay, let's suppose that button 4 got pressed. Then this would be a 0, and these would all be 1s. Okay, then this would be a 0, that would be a 1. This would be a 0, this would be a 1, and the output would be a 0. Okay, so cascading zeros. So if any button gets pressed, this is going to flip to a 0. Yes. Okay, so if we had wired the buttons using pull down resistors instead of pull up resistors, okay, then we would use OR gates because we would be going from 0 for not pressed to 1 for pressed. But we're sort of backwards, and like you guys learned in discrete math and stuff, what's sort of the logical opposite of OR? And in some sense, right? The or an and of the knots is the or of the knot of the or. Yeah, Rippy.
So, is there a way to get a result of these both resistors?
That's just the way he chose to do it. No.
Like
I don't think it really matters. So I think we could have done pull downs instead. Okay, so the difference between pull up and pull down, if you don't know that terminology, so the pull ups, these things, these data lines are tied to plus 5 volts through a current limiting resistor, and it's only when the button is pressed that they're shorted directly to ground. I could have sort of flipped this so that the resistors pulled the circuit to low, and that so I could have put ground here and plus 5 volts at the other end, in which case we call those resistors pull downs instead of pull ups. It's just which way is the logic. Okay, does it really make a difference? No, but if we're going to keep everything wired the way he already has it in his schematic, then, and without completely reinventing the wheel, then we would need to use AND gates. Okay, yes.
On the note schematic, the PCBs you got, how much of this is on the PCB and how much is not?
Everything is on the PCB,
Everything.
including the buttons, but not these AND gates. Okay, so the AND gate is something that we won't be able to fit onto the PCB. I'll have to redesign the PCB. Okay, so what that means is the way that the schematic is designed right now, the button pressing never triggers interrupts.
Could you just like take some wires and put them all in the same solder part with like the chip?
We might be able to make some room, or like throw an extra daughter board on or something. Okay, we could ghetto do it, but yeah. Okay, but back to Ben's schematic here. Okay, is right now the way that this is configured is such that the way you would detect a button press is to actively read the bits PA0 through PA4 and just see what they are. Okay, and if a given bit is a 0, that means that corresponding button is being pressed and otherwise is not. Okay, but you would have to go in and periodically, in the case of your program, check. Hey, all right, let me check the buttons now. Let me check them 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 now. Okay, which is kind of where we started the discussion, right? You could do that, or you could do what I'm suggesting here, which is that we add a series of AND gates. Okay, just a second, Cole. And we tie those AND gates into the output of all of them into CA1 and configure CA1 so that on a falling edge, where it goes from logical 1 to logical 0, we use that to trigger an interrupt. And then we read to see which buttons were being pressed at the moment the interrupt was done. We clear the interrupt flags when we read it, and therefore that surfaces the interrupt, and we go back about our merry way. Cole's hand was doing the like.
You just said that we go back and read.
We add an AND gate.
You go back and read which one caused the interrupt. How does that work?
Oh, so there's a register inside the 6522 that if we read it, it will tell us what all 8 of the PA bits are. So we just read that address, that register, and we get, so, okay, here's what buttons were being pressed. Because that we need to tie, okay, let me back up. So how do we know we need to go reading what the buttons, or what the PA stuff was? Because CA1 changed level. How does CA1 change level? That thing, right? If I didn't have that thing, I wouldn't know that a button has been pressed or not. I would just have to continually check, has a button been pressed yet or not? This basically, by changing the level of CA1 from high to low, so a negative, a falling edge, that will trigger an interrupt, which will go to the processor, and the processor is like, right? Okay, then, yeah, it's kind of like, this thing is basically saying there are 5 pull stations throughout the building, right? And I want the fire department to get called if any one of the buttons gets pressed. And then they're going to come check and they'll say, oh, shit, somebody pulled a fire alarm somewhere in this building. Let's go look and let's check all 5 of the pull stations and figure out which one was pulled.
I found one of the
You did. Okay, don't actually go pull it, right? Okay, but that's basically the analogy here, right? Is like the buttons are like the pull stations. Okay. So actually, I have gotten to trigger the fire alarm in this building once before. No, I have. So this was actually okay. So there are very few vices I have in my life. Okay, but one of the things that I have always had the urge to do, uncontrollable. Well, it is controllable, but very strong urge, is to pull a fire alarm. I've always wanted to do it. Okay, but I know better because that's like whatever. Okay. Yes. Okay. And now, and I have fortunately never been in a situation where there has been a fire such that I've needed to pull a fire alarm. Okay. Well, you could. So, did any of you know Professor Madsen? So he was in physics for a number of years and, no, don't think so. Okay. So he happened to be the chair of the safety committee. And one of the things that periodically needs to happen are fire drills, right? To make sure that the equipment, in fact, is working correctly. Okay. This is a normal thing, right? Huh? It's been a while since we've done them. Okay. Well, partly because we don't want to interrupt classes. Oh, well, that sounds like something Rippy might do or have done, right? So anyway, so I'm telling him about this, that I've always wanted to pull a fire alarm. Okay. And so like 2 years later, he comes up to my office and he's like got this evil grin on his face. He's like, "You want to pull a fire alarm?" And I'm like, "Hell yeah." And he's like, "We're about to do a test. Somebody has to trigger it. Do you want to do it?" And I'm like, "Sure." So we go down to the basement to where the control panel for the fire system is, and there's like a test button, right, that triggers it. And it wasn't as glorifying as a pull station, right? It was just a button, but I did get to at least trigger a test. So, but they know that it's a test because, of course, you talk with them in advance and so on, right? So they know that there's a drill going on, not the real thing. And
Until the drill actually turns out to be the real thing.
well, in which case, this is why we also have phones and there's a button that's like, no, this is actually a fire. We're not just testing. Um, anyway, so yeah, so essentially that's what the interrupt, the CA1 line, okay, which right now in the schematic has nothing connected to it. Okay, that's like not connecting our circuit to the fire department. Okay, so what if we had the fire department set up this way? What they would have to do is like every hour go around to every pull station and check, has it been pulled or not?
That sounds
That's
really time consuming.
Well, it would be, right? Okay. And even if they were checking every second, has it been pulled or not? Uh, our button presses are pretty quick. Okay. This is where the fire metaphor is going to break down. But like, is it possible that you hit a button and half a second later it's no longer pressed? Yeah, that could totally happen. And so if you're only checking the buttons every 1 second, you might miss something, okay? But by having this extra thing connected straight to the fire department, this means that the fire department doesn't have to continually check on campus until that signal flips. And then they know, hey, something just got pulled. Let me go figure out what's going on. Okay?
So it kind of feel like if all these, if all five of these things were like a light that was on, and then CA1 is basically
If something turns off.
if you got a miserable level.
Yeah, exactly. Okay. Um, yeah. And then, yeah. And then the processor, right, once you read and figure out which light bulb was out, that resets the interrupt because it's like, okay, yes, I know that this one is out, and then I'll deal with it. Well, then the buttons could change again. Okay. Now, the other thing, though, is so you remember CA1 can be configured to trigger an interrupt either on a rising edge or on a falling edge, but not both. And that's a good thing because do we want to trigger an interrupt if our fire alarm monitor goes from a 0 back to a 1? No, that just means that buttons stopped being pressed. Okay, and at least right now we're configuring this thing where we want to know if a button is pressed, we'll do something, and if a button ceases to be pressed, do we need to do anything based on that? No. Could we? Yes, we could. Well, yes, but the CA1 pin is only capable of determining rising or falling, but not both. Okay, we'd have to use CA2 and do a little bit of extra work if we wanted to detect either edge. Okay.
So all this is basically solving the OG problem of like
how do we know?
Holding on the button and getting like 1,000 numbers.
Yeah, well, sort of. Yeah.
Hopefully we get to number 1.
Yeah, well, okay, so Ben's video, what he does is he has a single button that he ties straight into CA1, okay? And what we're doing is basically extending that and combining it with the 5 buttons, okay? So what this means is with this extra, and I need to make a new version of this schematic. I'll see if he has the original of it that I can modify, okay? By adding this AND gate, and it's actually perfect that there's 4 of them, because how many are on each of these chips? 4, right? So there's 5 buttons, but how many AND gates do we need? We only need 4 AND gates, okay? And that's perfect because how many AND gates are on one of the 7400 series chips? It's 4 dual input, single output. Okay, now to Rippy's point, they do make quad input AND gates, okay, which we could have used here, but we don't have any of those. We have the dual ones upstairs, and so let's just use those.
I was more asking if you could just, okay, so the diode thing, okay.
I know what you're talking about, Rippy.
Can I not do that?
No, don't do it.
Okay, so like, when does like the speed come in?
Well, okay, maybe not until we're operating at frequencies above 1 megahertz.
So like, you're saying
it'll probably be fine, but
so if I have like an AND gate and 2 inputs here and then 1 input here, like that and then out, versus 2 AND gates, 1 1, or no, 3 AND gates, 1 1 and then 1, why would that be faster?
clock skew. I mean, and gate delay, right? I mean, the gate delay from this at the frequencies we're operating at is going to be negligible, so you won't have to worry about it. But yeah. Okay. Well, so right. Okay. So why do we need all of this? Okay. The reason that we needed to go through all of this is because what's sort of the ultimate breadboard project, right? We've bifurcated. You've got the breadboards, and hopefully you're going to eventually get the freaking things working. Cough. Okay. And then secondarily, we also have you guys wrote some Fibonacci code, right? Okay. All right. So how could we bring these things back together? Well, what about if we use 2 of the buttons as like up and down arrows, and anytime you press, so you start with the number 0 on the screen, and anytime you hit the button that you're going to assign to be up, it will increment that number by 1. And anytime you hit the down, it will decrement that number by 1. So I could come along to my little thing and I could hit the button like until it says 8 on the screen, and then I could choose a third button to represent enter. And if I hit enter, then it will say, okay, I'm going to compute Fibonacci of whatever is currently on the screen and then output that value to the screen. Well, guess what one of your assignments is? Yeah? Okay, so vamoose. See you guys on Thursday.